Now at this point, we're ready to simulate the process of random reproduction and let these random individuals produce eggs and sperm, and then we're going to join the eggs and sperm to produce offspring genotypes. So this grid here is going to be for simulating the offspring population. First, we're going to determine a random mom, and we'll use the RANDBetween function for that. Our bottom number will be 1, and our top number will be the size of the parental population. And let's anchor that and pull that down. Now, at this point, we've drawn random mom number 5. So here she is. And note that the random number, the individual, can produce both eggs and sperm. So we're dealing with an individual that can produce both kinds of these sex cells, and it's certainly not the tiger that Jed mentioned, but it's good enough for us to get a handle on what drift is, so bear with us here. Here's individual 5's genotype. It's A1A1. And so when this individual undergoes meiosis, her egg will have an A1 allele. However, if an individual is a heterozygote, then their egg or sperm can contain either an A1 or an A2 allele, depending on the luck of the draw from the process of meiosis. And we're going to be entering an equation in cell E9 that will let us generate a random gamete from the individual that's been selected, and we'll do the same thing for the dads. Now, I'm going to warn you, this equation can be a little bit long. I'm hoping I can walk you through it. We're going to set it up this way as opposed to the way we did it in the Hardy-Weinberg spreadsheet, because that way we can fully let any individual reproduce, and what ends up in the egg and the sperm is 100% random. So let's try this out. Remember, we said in order for us to generate a gamete, we need to either take the left side allele or the right side allele, and that would be placed in the egg or sperm. So we want this equation to return either the left 2 digits or the right 2 digits of the associated genotype. And we're going to use an if function to do that. So first thing we're going to do is to ask, is a random number less than 0.5? Because we expect that half of the time the gamete will have the left portion and half the time it will have the right side portion. Now if it's true, we want to return the left 2 characters, but it needs to be associated with the random mom's number. So if it's true, we're going to use the left function, and the left function is going to tell us, it's going to find, we've specified the cell, and then we specify with a comma the number of characters. So we have to enter something before the comma. For now though, just bear with me. We're going to draw a random number, and if the random number is less than 0.5, we're going to return the left 2 characters associated with the random mom. Otherwise, we'll return the right 2 characters associated with the random mom. Now here's the tricky part. Right here we need to find the random mom. And if you remember from the Hardy-Weinberg spreadsheet, we used the VLOOKUP function. And I'm just going to type that directly in here. So VLOOKUP, we're going to look up, and I'll open and close that function. So here is the lookup equation, and inside those 2 parentheses we're going to enter the 4 VLOOKUP arguments. The first argument is, what are we going to look up? We're going to look up the random mom, comma. The second argument is, what table are we going to look up the random mom? We're going to look up the random mom in the table from columns A through column C, all 500 individuals, comma, when Excel finds that random mom, we want Excel to return the value in the first, second, third column of that table. So that's going to go right there. And the last argument for the VLOOKUP function is false because we want an exact match. So I know this is fairly complex. We're nesting functions within functions, but in fact this will make our spreadsheet very, very flexible for us to play around with it when we get to the sandbox. So now we can copy this VLOOKUP function and now place it into the third argument here, and we'll just paste that in, and now we have a random gamete from our randomly selected mom. I hope that makes sense to you. Before we copy this down, we need to anchor the references in the VLOOKUP table. And at this point we can carry it through. And what we're going to do now is to find and just make sure this all looks correct. So here's random mom number 10. She's A2, A1. And the spreadsheet's returning, by chance, an A1 allele in her egg. Here's individual number 3 as the second random mom. It's A2, A2. Here it is again. And so individual number 3, this time she's A2, A1. And by chance, the spreadsheet is returning an A2 allele in her egg, in the gamete. So if we copy this through, we'll find that when a random mom is a homozygote, like in this case, the random mom is number 1, her genotype is A2, A2, so her egg must contain an A2 allele. Now I know that's a lot, but take some time with this, see if you can digest how this nesting occurs. Again, we've chosen to do this because it makes our spreadsheet very flexible for handling problems that we'll tackle in the sandbox. We can use this exact same formula for handling the random dad. So let's first get the random dad, and we're going to use the RANDBETWEEN function again. The bottom number will be number 1, and the top number will be stored in cell B5. We'll copy that down, and then we'll copy the formula in cell E9, and we'll paste it in there for the dad as well. And if we click up in the formula bar, we should see that the references are correctly tagged. And at this point now, any individual can mate, and anytime that they do mate, there's a random chance of which allele is passed on in their sex gamete. The next step is just to join the egg and the sperm, and we'll do that by concatenating the two, and now we have some offspring genotypes. Just like we had for the parental genotype, we need to enter the number 1 if the offspring is counted. And so we'll use another if function here, and we'll simply ask, is the individual less than or equal to the number stored in cell C5, anchor that. If it's true, we'll return the number 1, otherwise we'll return the number 0. And we'll press OK, and then copy this through. So don't let these individual numbers here fool you. These just are a way for us to identify the different individuals. So individual 1 for the parents is not the same as individual 1 for the offspring. It's just a way for us to identify who we're counting in the parental population and who we're counting in the offspring population for these random genotypes. Now at this point, we're able to summarize the genotype numbers and the allele frequencies for the offspring population, and you'll be using those same formulas we've used for the parental population. So put your video on pause, fill out these entries, and then we'll come back and we'll pick up and start to simulate the population dynamics for genetic drift. So I'll see you in a couple of minutes. Okay, welcome back. Now, your results will look different than mine, but let me just walk you through how my calculations ended up. I started off with a parental population size of 10 individuals. I assigned them random genotypes based on the frequencies specified in cell D5. Then, from this list, I chose at random a random mom and a random dad. And for each one of those, we took their genotype and we simulated the process of meiosis and went through the process where the egg or the sperm is now holding a single allele. We then join the egg and the sperm to create the offspring genotype, and then we calculate our total numbers and our allele frequencies. At this point, we've actually simulated genetic drift. Here's why. We started off with a parental population with an allele frequency of 0.35. We let the population mate at random. It had no other evolutionary forces working on it. The mating was random, there was no natural selection, no mutation, no gene flow. We've covered all of our bases as far as evolutionary forces. The only thing that is keeping this population from staying at 0.35 is this small population size. The population frequencies changed from 0.35 to 0.4 from one generation to the next, and by our definition of evolution, that is considered to be an evolutionary change. Now we can simulate this process again, and in some cases you'll see that the populations stay the same from one time period to the next. If I press F9 once again, now I'm simulating some change. This change is more dramatic in small population sizes compared to large population sizes, and we can prove that to ourselves by a simple little experiment. Let's change the number of parents and the number of offspring to 100. And now, as we press F9, we're going to see that there might be some changes from generation to generation, but they're not nearly as dramatic as we saw with the case of 10 individuals. And I'll bet that you can sense that we're going to do some simulation here, and you'd be right. But before we do that, let's try a very large population, 500 individuals producing 500 offspring. And now let's press F9, and you'll see that these numbers are actually very close indeed. So the key concept here is that drift results in a change in allele frequency over time, and that's strictly due to the fact that we're randomly assigning and selecting eggs and sperm to create the offspring population, and that by chance, because the numbers are small, we might deviate more than what we expect as far as the allele frequencies are concerned. So that, in a nutshell, is genetic drift. Now, in lecture, Jed presented a time series where you start with a population at time step 0, and then you track the frequency of the allele population of the A1 allele through time. So if we started off with 0.392 and then moved to 0.38, then we would record those through the time steps here and track the frequency of the A1 allele through time. We'll do that in the next video, and there we'll be building a few macros. So I'll see you there in just a few minutes.